All right, so let's continue on with the Epoxides chapter, and let's do a little practice. Let's say I've got this starting material, and I want to make an epoxide. And if I make the epoxide, I'll have this oxygen inserted across that double bond. What reagent do I need? Yes, MCPBA or what? Or peroxyacetic acid, or if you really want to get fancy, you could do the sharpless epoxidation, where I showed you the chiral catalyst. However, this one wouldn't be an antioselective because we don't have an allylic alcohol. Either way, you need some sort of peroxy acid to form an epoxide, right? The previous chapter we said if we add acid, we can protonate this epoxide. Oh, let me clean this up a little bit. All right, and then if we have a nucleophile, which side will the nucleophile attack? Or actually, let's do nucleophile without a charge. Which side will the nucleophile attack? More substituted side. When we covered the halohydrogen reaction, we specifically said that the water will always add into that more substituted side. The story gets a little bit more complicated, and that's what we're going to cover today. But let's finish drawing this product. The key thing to remember is you always get anti-addition, and usually there's some sort of deprotonation step. Let's take a step back, though.
Why is the...
Oops, thank you. That was a test. You guys passed. All right. I was going too fast. Nucleophile is attacking this side. Now let's take a look at the carbon that nucleophile attacked. What sort of carbon is that? It's a tertiary carbon. So if we look at this carbon, it's a tertiary carbon. Anytime we do acid-catalyzed opening of epoxides, the nucleophile will attack a tertiary carbon. The question is why? Why do you guys think that tertiary carbon is going to be attacked? Yeah, so oftentimes there's this dueling feature in chemistry, right? If I'm a nucleophile, I could say, well, I really don't want to attack that carbon because sterically it's blocked by two methyl groups. But then the other part of me says, well, when I attack that carbon, I go through a more stable transition state. So we've got two different things to consider. And in this specific case, nucleophiles will attack the tertiary carbon due to the stabilization of that transition state because it's more substituted. So let's make a little note. Oop. With acid catalyzed ring opening, your nucleophile will add into the tertiary carbon. Now there's a little bit of a hiccup with this, and that is when we have secondary carbons versus primary carbons. So let's take a look at an example. So in this example, we're going to use a different starting alkene, and I'm going to make this into an epoxide with MCPBA. And this time we're going to again add acid. So we'll protonate this epoxide. Now we've got a choice as a nucleophile. Are we going to attack the less substituted side simply because it's less crowded, or are we going to attack the more substituted side because it goes through the more stable transition state? And it's not immediately intuitive. When we were covering the halohydrogen reaction, I told you guys always attack the more substituted side. It's not always cut and dry like that. In this case, quite often you will attack, the primary carbon, simply because it is more accessible, and secondary carbons don't have that much resonance or hyperconjugation stabilization. So in this case, your nucleophile will actually add to the less substituted side. And so let's make a side note of this. With secondary carbons, there isn't that much stabilization. So the nucleophile will attack the primary carbon, since it's less sterically hindered. We've changed the regiochemistry, but we haven't really changed the stereochemistry, right? The nucleophile is still going to add anti to the alcohol, and you're going to get an inversion anytime you do an SN2-like attack.
Is this only for uncharged nucleophiles?
Yeah, in this case, why don't we usually have NU that could be a strong base, too? Not quite. What's the fastest reaction in chemistry? Acid base. So if we have in a really good nucleophile, it's also a good base, we'll just deprotonate our epoxide before it can add in. But we're going to get there because you can open epoxides under basic conditions. So these two, if you look at these, both of these reactions that I just showed you are acid catalyzed ring opening, meaning we're going through an epoxide that's already been protonated. Does that make sense? So we've got this duality. We have to look at substitution and sterics when we're looking at ring opening of epoxides. Go down. All right, so now the question is, well, what if we just skip the acid step and throw in a super strong nucleophile? Can we ring open this? What do you guys think? We might be able to. It depends on the strength of the nucleophile, though, right? So with an SN2 type reaction, we have to have a really strong nucleophile. We covered that first term. So anytime you see ring opening of epoxides with a nucleophile and no acid, that nucleophile has to be really strong. So let's take a look at base catalyzed ring opening, or base, I guess it's not catalyzed. So ring opening of epoxides without acid. We're familiar with the acid catalyzed ring opening. So let's take a look at this example, and I'm just going to make it super generic. We're going to add MCPBA. We're going to make our epoxide. And this time we're going to use a nucleophile that's very strong. All right, if we have a super strong nucleophile, something like a Grignard reagent, which side do you think it's going to add into? Yeah, the less substituted one, right? So if we look at this, we could say, all right, this nucleophile, come on. Sorry. This nucleophile is going to add into the less substituted side because this is really reminiscent of an SN2 reaction, right? SN2 reactions always prefer to go after the less substituted carbon because that backside attack is a lot more exposed. So let's even make a note where this is SN2-like. If we look back up at the reaction above it where we had acid, this bond up here, this bond is highly polarized. Meaning it's not a very strong sigma bond. So in this case, we're not looking at an SN2-like reaction. It actually has a lot of characteristics of an SN1 reaction too. So down here, we're primarily doing an SN2-like attack, which means we're going to favor the less substituted carbon under all conditions. So let's draw our intermediate. And we've got this oxygen with a negative charge, so we've got an alkoxide. What do you think the last step is? Yeah, we're going to quench this with some sort of acid. We can even use water as a weak proton source. So now we've got our alcohol that is adjacent to our nucleophile, and we've got our final product. So let's make a note of this and say, when no acid is used, a strong nucleophile will always add to the less substituted side. Of the epoxide. Does that make sense? So it's getting back to chemistry from first term, basic SN1, SN2 chemistry. When we're dealing with an SN1-like reaction where we really want to stabilize that carbocation, or at least partial positive in the transition state. But with SN2, we really want that backside attack to be most approachable.
Size?
So in this case, because, I'm trying to think. So you're arguing what about the size of the nucleophile?
No, you wrote less substituted size.
Oh, side. Sorry. Thank you. So it'll attack the less substituted side of the epoxide. But I made my own question. If the nucleophile is bulky, do you think this reaction rate is going to proceed very quickly? No. So in this case, small nucleophiles will attack the epoxide a lot more quickly. In fact, if you go through your textbook, it talks about how epoxides are often used as cleaning agents for surgical equipment, because if you take something like an epoxide and you put it into surgical equipment and you've got DNA with a bunch of amines around, what do you think could happen? The amines could ring open the epoxide and you would end up sterilizing that equipment. So epoxides are quite often used in sterilization of medical equipment. They're also really useful synthetically because now we can make an alcohol and we can make potentially all sorts of different bonds. This nucleophile could be a whole variety of different things. So let's make a little chart where we can map out what sort of reactions we can do with these epoxides. I really like making reaction maps just because it gives you a nice visual way to see all the different directions you can go with the starting material. And so for this starting material, I'm going to pick a basic epoxide. And let's say I want to make an alcohol where a thiol group is in the beta position. So this would be a beta mercapto alcohol. The question is, how would we get there? What do you guys notice about the position of the alcohol? Is it coming off the more substituted side, less substituted side? More substituted side. That means that this sulfur down here must have been our nucleophile, right? That it added into the less substituted side. So do you think this was under basic conditions or acidic conditions? Basic, because with basic conditions, we always favor that less substituted side, right? So in this case, we have to pick some reagents. The question is, what would an appropriate nucleophile be to install a thiol there? Yeah, Nash. I heard somebody say it in the back. So this goes back into first term chemistry where I said that sulfur with the negative charge is a really good nucleophile, right? It's got this giant electron cloud. That means it's definitely going to react with that electrophilic carbon, and because this is under basic conditions, it's going to favor that less substituted side. In the second step, we're going to add in water, and that will just quench and give us our alcohol. All right, what if we want to do a nitrile that is beta to an alcohol? What reagents will we use? What do you guys think? Please don't say hydrogen cyanide. Why wouldn't we use hydrogen cyanide? Well, yeah, number one, we might add to that more substituted carbon. Reason number two is we might kill ourselves on accident, right? Sodium cyanide, the salt, won't kill you as easily. So in this case, we can use sodium cyanide. That carbon has a negative charge on it. That means it's a really good nucleophile. It's going to go after that less substituted side and ring open it, and then we can treat this with water and we can quench it. So now we have a way to install nitriles pretty easily. We can also make ethers. What reagents would we need for ethers? Let's say we want a methoxy group coming off that position. What reagent would we use? And Mondays are rough. Got sodium. And then we would want sodium methoxide, right? So the oxygen, in this case, would have the negative charge and it would attack in. We could quench this with water and get us our final product. We can also do this with a Grignard reagent and just install a carbon directly. So let's say we do RMgX followed by water.
Is it H2C?
H2O. And this would give us our Grignard reagent, which is a great nucleophile, and that will add in here. So this is our new R group. And last but not least, we've got another really nice reaction where what if we want to just install a hydrogen? Question is, how can we get a hydrogen to act as a nucleophile? This is a little bit tricky. So hydrogen, in order to be a nucleophile, must have a negative charge, right? So we've seen NaH, but NaH is a really, really good base, but not a very good nucleophile. Do you remember me saying that with the SN2 chemistry last term? I said it's a really good, strong, non-nucleophilic base, but we just covered another reagent where we had hydride react with the molecule. It was in the name. Yeah, so sodium borohydride was a hydride source. What was the other one? Yeah, lithium aluminum hydride. So in fact, if you wanted to do this, you could do lithium aluminum hydride followed by water. And the hydride will come off of the lithium aluminum hydride and get installed onto that less substituted side. So now you can go from an epoxide all the way back to an alcohol. The main thing to remember is that all of these up here are under basic conditions, or under non-acidic conditions, I should say. And we can get completely new regiochemistry if we do this under acidic conditions. So let's do the same thing down below, but this time we're going to make a reaction map where we do this under acidic conditions. All right, so let's say I add just aqueous acid, H3O+. What will this give us? Not everyone all at once. This was similar to our Chapter 9 reactions. So if we had an alkene, we treated it with MCPBA followed by aqueous acid. We get what? Yeah, an anti-diol, right? So in this case, we can add in our alcohol, but it will get attached onto the more substituted side. Not that it really matters, because in this case we've got a diol. All right, let's do another one. Let's say we do acid that's catalytic, and then we add in a thiol. What do you think our product will be? Does anybody remember the name of sulfur that's bonded in between two carbons? Sulfide. So in this case, we can actually make a sulfide out of this. So we've got a new sulfur carbon bond. It's pretty straightforward. We can do the analogous one with regular alcohols, where again we add acid followed by our alcohol. And this time we get our alcohol to add anti. And then last but not least, we can take something like HCl or HBr, and that will add our halogen on the other side. In this case, we don't need catalytic acid because we're just throwing in a plain old acid. Scroll up.
No, I'm sorry.
Sorry, I forget in the back, it's hard to see. And all of these are under acidic conditions. All right, so what we're going to do now is I'm going to pull some practice problems, and I want you guys to try to anticipate what the regiochemical outcome will be and try to predict what the product will be. So include all the stereocenters if they're relevant. And if you want, you can work with a neighbor next to you, but I'll throw down a couple example problems. So this one we're going to add in catalytic acid, followed by ethanol. And then I'll put down a couple more practice ones. Let's do these two as practice. I'm going to color code our carbons too, just for fun. All right, in the top one, if we look at problem number 1, we've got a blue carbon and we've got a green carbon. We've got acid around, so what carbon do you think the nucleophile is going to add onto? The blue one or the green one, and why?
The blue one.
Blue one, why? Tertiary. Anytime you see tertiary under acidic conditions, that's going to be the site of attack. So let's go through and draw this out. So I'm just going to draw this as H+. Now that we've got this protonated, all right, ET, we've got ME. Now we've got ethanol.
Just skip a step.
Oops, sorry, I forgot to tag my proton on. There we go. Now we've got our ethanol. We said our ethanol is going to add into this more substituted side. Which means this alcohol is going to be sticking up. The ethanol that got added in is going to be sticking down. That oxygen is going to be protonated. This methyl group over here got unchanged. But what about the carbon where the ethanol attacked? It's going to be inverted, right? So that ethanol is still going to be a wedge. Or sorry, the ethyl group. And I'm actually going to abbreviate this pH just to save some room. So that phenyl group got flipped up, that ethyl group got flipped up. We have to remember to invert stereochemistry. And then last step will just be our deprotonation. So now we've got our ethoxy group anti to our alcohol, and we've got our methyl group down here. We've got our ethyl group sticking up, and we've got our phenyl over here. Does that make sense? Raise your hand if you're like, this is rock solid. All right, let's do more practice.
Where does the pH come from?
The pH? So oftentimes chemists like to use shorthand. pH is just short for phenyl. So if you ever get tired of drawing hexagons, you can do pH or CY for cyclohexane. The key thing to remember is the regiochemistry is important, meaning what carbon are we adding to, and the stereochemistry is important. You have to remember to invert the stereochemistry. Yep?
What about the hydrogen in the last step? Is it gone, or do we add one more hydrogen?
So typically with these reactions, like in lab, we'll do an aqueous workup in a SEP funnel, and it will get a proton, or it'll be deprotonated by solvent, usually water, in the workup.
So actually the oxygen of the water will attack the hydrogen, and then the electron pair will jump to the oxygen?
Yeah, exactly. This is a pretty acidic proton. Let's see if this works.
But why roll the H there instead of writing water?
So in this case, I didn't specify water. It's just important to remember that oftentimes the last step of a reaction is deprotonation to get to a neutral product.
Okay.
Let's do the next reaction, though, with sodium cyanide and water. See if you can draw out the full mechanism for this. Shoot. There we go. Let me change my batteries in my pen here. So what carbon do you think the cyanide's going to attack? The blue carbon or the green carbon? Blue carbon. Why are we attacking the blue carbon?
Because it's less substituted.
Yeah, exactly. The carbon's a lot less substituted. So in step one, we've got sodium, we've got carbon that's negative. What sort of bond is between carbon and nitrogen? Triple bond. Oftentimes people see CN and they're like, oh, it's CN, that's a carbon-nitrogen single bond. Not so much. We got to remember that CN minus is actually more appropriately drawn as carbon, triple bond, nitrogen. This carbon has a lone pair. That means this carbon's negative. So this nitrile will attack our less substituted side. It will ring open this. We've got O minus. In this case, this methyl group is still going to be shown as a wedge. And then in step two, we've got our water that will get deprotonated. And we've got our alcohol over here. All right, let's do another practice one. This time more complicated. So in this case, because I showed you an epoxide with set stereochemistry, you would only get one product. If we made this epoxide as a racemic mixture of enantiomers, then you would get a mixture of enantiomers out. So that's one thing to remember. All right, let's do one last one. This time, I'm going to do this, and it's going to be a multi-step problem. Oh man, tough stuff. Let's try to figure out how to get from this alkyne to this alcohol. And I'll give you guys a hint too. You can use other sources of carbon. Epoxides are a really good source of carbon. I'll give you guys a hint too. Just like we did before, we can label these. We can say, all right, we've got a green carbon and a blue carbon. Those are our adjacent carbons, right? So this was our alcohol that came off of our epoxide. Whoops, I'm forgetting a carbon. Shoot. Sorry, guys. Let me redraw this. So 1, 2. There we go. I was missing a carbon. So now the question is, how can we get this entire group to add on as a nucleophile? Does anybody have an idea?
Treat it with the strong base.
So you're saying treat the alkyne with the strong base? Okay, so let's try that. Let's say, all right, so proposed synthesis.
How about adding the rest of the carbon chain into the right side of the alkyne and open?
Well, let's try a couple different routes. Let's do the first one that Ramon suggested. So Ramon said, all right, let's take this alkyne. We've got a proton. If we treat this with sodium amide, we'll form our acetylide ion, right? All right. And then what reagent would we need to give us that blue carbon and green carbon? Yeah, a simple epoxide. This is called ethylene oxide. It's commercially available. You can buy it in a bottle. It's pretty nice stuff. So in this reaction, we could have this add in, ring open our epoxide. And when we do this, we now have an alkoxide down here. We've got our new carbon-carbon bond. All right, so we're getting there. Now what? Okay, let's protonate our alcohol first, just for fun. We'll just add in water. So now that we've done that, we can deprotonate our water. And then last step to get to our product was what? It was H2 and palladium, right? So in this case, it can look pretty frightening and scary, but if you do see an alcohol, there's usually some sort of reaction you can do that involves an epoxide to get there, right? So alcohols are a good new signal we have for retrosynthesis, where whenever we see an alcohol, we can work backwards. What was another way to install a carbon functional group into an epoxide? A Grignard reagent, right? Could we turn this alkyne into a Grignard reagent? If we try hard enough, we can do anything, right? So let's say alternate synthesis. The alternate synthesis would be to turn that alkyne into a Grignard. Does anybody have a proposal for how to turn that alkyne into a Grignard? Couple different ways.
H2 and Lindner's with alkyne and
Okay, so H2 and Lindner's, if we did that with our alkyne, we could turn our alkyne into an alkene. And then how would we go from our alkene to our Grignard? Oh, yes. So let's go do this. We've got some nice review. So let's do H2 and Lindner's. Will we get cis or trans, or does it matter? We will get cis, but in this case, it doesn't really matter, right? We could do dissolving metal reduction if we wanted. Okay, and then we've got HBr, and we've got peroxides. 100% agree. If we do this, now we've got our bromine. How can we turn this into a Grignard reagent? Magnesium turnings, right? So we do magnesium metal. So MgBr. Now if we react this with ethylene oxide followed by water, we can now get let me give us more space here. We can now get to the same product. All right, so there's a couple different ways we can alkylate an epoxide. We can either use our alkyne directly, deprotonate it and use it as a nucleophile, or we can change our alkyne into some sort of nucleophile. Does that make sense? Okay, that might be helpful for the pod. Hint, hint, wink, wink. All right. Like what I did there? All right, so let's continue on to thiols and sulfides. We're getting close to the end of this chapter. The exam will go up through chapter 14. Yes. All right, so thiols are the sulfur analogs of alcohols. Meaning if you take an alcohol, just swap out the O for an S, and you've got yourself a thiol. So let's do a little bit with naming of thiols, and we'll compare it to the naming of alcohols. So let's take these two analogs. I've got the alcohol on the left, I've got the thiol on the right. Let's name the alcohol first. What should this alcohol be named? We'll find the longest carbon chain. Do I want to go 1, 2, 3, 4? What's wrong? Yeah, alcohol gets highest priority, so we go 1, 2, 3, 4. Okay, so we've got a methyl group off the 3 position. That helps. So what should this be named? So 3-methyl 1-butanol. Okay, so pretty straightforward. The main thing with alcohols is we end in this "all" suffix. That's what tells us it's an alcohol. If we try to do this with a thiol, we still number it the same. It's still 3-methyl. And then we do 1-butane thiol. So this "O-all" suffix for alcohol essentially gets changed to an E followed by a thiol. So we do want to include the E coming off of butane, and then we add a thiol onto the end. It does get a little confusing when you have multiple functional groups present, especially with thiols. So let's take a look at one of these examples. So let's say we've got this one. The main thing to remember is that alcohols take priority. So when we number this, we still want to number starting at the alcohol position. So we can go 1, 2, 3, 4 from right to left. Now because we've got an alcohol group on there, we can't have an ane thiol suffix. Instead, we look at this alcohol, or this thiol, and we actually call it a mercapto group. Yeah, it gets into weird Latin origins. Mercaptans used to be called thiols, or thiols used to be called mercaptans, so mercapto groups are analogous to thiols. So when we name this, we would actually call this 3-mercapto, 3-methyl, 1-butanol. This mercapto group is now our placeholder for where that thiol is coming off.
What if there's two thiols?
Oh, then you run into crazy situations. I believe it's dimercapto.
Okay.
And if you've got other functional groups like ketones and stuff like that, then the numbering priorities get crazy. Let's stick with the simple naming. It's complicated enough as is, I would argue. So let's talk about preparation. So let's do the preparation of the thiol analog. Let's say I want to add in the thiol where that bromine used to be. What reagent should I use? NaSH. NaSH. So in this case, sulfur is a really good nucleophile, right? We saw this last term. We actually did reactions like this last term where the sulfur can do that backside attack, give us our thiol, and now we've got sodium bromide as our salt. So it's pretty easy to make thiols via SN2 chemistry. We saw a bunch of it last term. Thiols are excellent nucleophiles. Are they good bases? No. Typically they're not very good bases because sulfur is so big it's actually okay with that negative charge. However, it's a pretty good nucleophile. We can even do reactions at secondary carbons because of this. So if we use NaSH, we'll still get an SN2. We won't observe E2 very much in this case because this just isn't a very good base. So not a good base. So what product will we get out? Same thing but inverted, exactly. So we have to remember our stereochemistry. However, we get no E2. E2 would have been the major product had we used something that was a good base. So in this case, thiols are nice because of that. All right, so now let's take a brief look at disulfides because they're important in biochemistry. All right, so let's say we have two thiols. These could be thiols that are dangling off of cysteine residues. What's cysteine found in? Not DNA. Not RNA. Close. You're narrowing down the biomolecules. Yeah, it's an amino acid. So it's found in proteins. And this is really important for how proteins fold. You could have two cysteine residues that are nearby in space. And if you oxidize these, they'll actually form a disulfide linkage. So this is very, very important for proteins. It's how proteins fold up correctly and how they retain their shape. And we can do this synthetically too. So if we want to do this synthetically outside of a cell, we can just add in sodium hydroxide, water, and bromine. I'm not going to go over the mechanism, but it's a nice way of making sulfides. So this is our oxidation reaction. And if we want to go the reverse direction and we want to go from a disulfide back to our thiols, we can do this by using HCl, and zinc. So this top one is an oxidation. This bottom one is a reduction. We're not going to delve too far into this chemistry, but I did want to show it for those of you guys that are going into biochemistry. The next thing I wanted to show you guys is a really brief reaction.
Can you scroll up a little bit for the
Yep.
oxidation?
The next one is a sulfide. So sulfides are analogous to ethers, but with sulfur instead of an oxygen. So let's take a brief look at sulfides. Okay. So I'm going to choose a generic sulfide. I'm going to choose R and then R prime as our two substituents coming off. The sulfur has two lone pairs. And we can actually oxidize this through a couple different states. We can oxidize it once, and then we can oxidize it again. Sulfur is a little bit odd. It's a little bit flexible when it comes to the octet rule. So if we look at the compound on the far right, we would say that violates the octet rule, and then we have to remember sulfur doesn't really behave like normal. In fact, those sulfur-oxygen bonds aren't quite double bonds. The reagents that are required to do this are sodium iodate, followed by hydrogen peroxide. And then, if you just want to go from this one to this one, you can just slam it with a bunch of hydrogen peroxide. The names of these are what I'm more worried about you guys knowing. This is a sulfide. This is a sulfoxide, because now we have an oxygen on there. And then the last one is called a sulfone. So you may occasionally hear these names thrown around in your textbook, and I wanted you guys to be able to place a functional group with the name that they're throwing around in the Klein textbook. All right, tomorrow when we come in, we're just going to do a bunch of in-class practice problems, but please come to class. Practicing in class is an excellent way of studying.